Hi everyone, my name's Emily Wade and I'm here with Ashley Russell and we're the engineering chicks and this is our presentation 2 for our digital simulation class and we're going to talk about Monte Carlo today. So before we really dive into Monte Carlo, we just want to lay some ground knowledge for you. So evaluating an integral, when evaluating an integral, you're finding the area under the curve of the given function. So what is the integral being evaluated? So in our particular example right here, it's actually a double integral, but right here, this function is what is actually being evaluated. And the integral is being evaluated. It's a function that you're trying to find the area underneath the given function of the curve that is produced when it's graphed. So just a little bit more about evaluating integrals. Sometimes you can't just do it, and that's because the integral that you're trying to solve, the function is just too complex. And an example of a too complex integral would be an integral with many dimensions. And so we can compensate for this flaw with just straight up integration by mathematical means by simulating data points that would find the area under the curve of the function when this function is overly complex. So now we're going to talk about expectation and what that means with integration and in Monte Carlo. So simply, expectation is just the mean value of a function. It's a value that you expect to get for your output given a random input. So you just throw in a random x variable, the expectation is what you expect the answer to be when you get the y value back. So it's a predicted value of a variable, and it's a calculated sum of all possible values, each multiplied by the probability of occurrence. So now we're going to talk about Monte Carlo, and you'll start to see how it's different from just regular integration. So Monte Carlo is an integral estimation because it estimates the expected value of the area under the curve, whereas normal integration, it's not an estimate. Monte Carlo, it's an estimate, but it's a good estimate. It's always close to the actual answer. And we have a couple questions that we were asked. So this first one here is this statement: we can estimate the value of any integrand, no matter how complex the integrand is, important, and why. So in the real world, real problems aren't always super simple and easy. They don't always have like this perfect integrand that you can easily solve. So being able to estimate the value of any integrand, no matter how complex it is, won't limit your ability to solve problems. And you can get answers to problems that aren't so cookie cutter. And then the second question is, what relationships do integrations, probability densities, and fissionable materials have in common? So this was a problem that we talked about a lot because it's super complex and it's not something that you can solve with regular integration. So there are a lot of different distributions governing nuclear fission events, and if you can find the expected value of those functions, you can then estimate the probability of certain events occurring, such as an atom splitting. So now we're going to answer the question, how can you use Monte Carlo to solve for complex distribution functions? So there's just some fairly simple steps that you can just repeat over and over again for different problems and come to the right answer. So first, you integrate the distribution function from 0 to x with respect to x. And then second, you set r equal to your integrated function and solve for that x. And third, using that solved function in terms of r, you generate random values of r to solve for the value of x for each iteration. And then fourth, you sum the x values of the iterations and then divide by the number of iterations. And then this gives you your expected value of the distribution function. And then how are complex distribution functions related to the mathematics behind determination of the yields of fissionable, fusionable materials? We kind of talked about this on the last slide, but the fission-fusion yields of materials can be modeled by extremely complex and by multiple different distributions. You can use those complex distributions to find the probabilities associated with the yields of fissionable, fusionable materials. So next we're going to go over into MATLAB, and we're going to show you a way to solve an integral using Monte Carlo and then just a regular way. And we're going to show you how to use Monte Carlo to evaluate the expected value of the exponential distribution in particular.
Okay, so now we're in MATLAB, and like Ashley said, we're going to show you kind of two different scenarios of examples of MATLAB code using Monte Carlo that we've kind of covered in our PowerPoint slides. And so this is just a simple integral that we're solving using Monte Carlo. And with this, you can see we're setting up our number of iterations. So that's the number of times we're going to simulate the solving of the integral. And then we generate a random x and a random z because this function that we're working with has both an x variable and a z variable as an input. And then to actually manipulate the function that we were given to solve it with Monte Carlo, we're going to use a method that we call factoring out. And we decide to factor out the standard normal distribution because that's kind of what our function reflected. And so based off of that, we can calculate the mu value, and that's going to look something like this. And you can see that the answer that we got was 6.2910. And we also have this integral evaluation check below it that just mathematically solves the integral function that we were given. And as you can see, these are very close in answers, only off by like very slightly. So you can tell that Monte Carlo has done a really good job of estimating the expected value for this integral. And then moving into our second example, this is the one that Ashley talked about with our methodology for solving a complex distribution. So we just selected the exponential distribution with a value of lambda equals 1 to just show the steps taken to solve a complex distribution. And so you can see here we've got it set up to where it goes through this iteration for Monte Carlo 10,000 times. And here we are evaluating the integral from 0 to x with respect to x. And then we are setting it up to where we solve for x. So we set r equal to what we got for the answer of the integration from 0 to x with respect to x. And we're solving for r in terms of x. So that gives us, I'll go ahead and run it so we can kind of talk through this. That gives us this value of negative log with 1 minus r. And so then we're going to generate random r values for the simulation randomness of the Monte Carlo actually aspect of this of solving this complex distribution. And so when we do that, our answer, as you can see, is 0.9841. And just looking at the randomness of this, we can run it a couple of times, and you can see that based off of the random numbers generated that it's going to be a slightly different answer. So this time we got 0.9914. And that is a very close estimate to the actual expected value of the exponential distribution. As you can see, we also did this with a regular integral evaluation of the exponential distribution, and we got that the answer is 1, which is fundamentally, we know that the expected value of the exponential distribution is 1 over lambda. And with our lambda being 1, that results in an expected value of 1. So I hope that we were able to introduce you to Monte Carlo well. And if you have any questions, you can leave them in our comment sections. And please tune in again for our next presentation video. Until then, this is the Engineering Chicks signing off.